Welcome to lecture 1.13. We have been looking at reduction of multiple subsystem systems, and we are going to continue that today. So we have seen block diagram reduction on the last turn, and we also saw how to draw the signal flow graph. Uh, and we saw the basic definitions related to signal flow graph, which included the definitions of path, nodes, forward path gain, non-touching loops, so on and so forth. So today we are going to see how to write down the transfer function from the signal flow graph using Mason's rule. So the rule is given here. The rule is that your overall transfer function, where CS is your output and RS is your input, is given by summation over K, Tk del K divided by delta. So K is the number of forward paths. So if you have one forward path, this formula will reduce to T1 del 1 by delta. If you have two, this formula will reduce to T2 del 2 plus T1 del 1 over delta, so on and so forth. Then we have the definition for Tk. Tk is the forward path gain, the gain of the kth forward path. So in this case, T1 is the gain of the only forward path that you have, that is 1, and here T1 is the gain of the first forward path, T2 is the gain of the second forward path. Delta is slightly complicated. Delta is given by 1 minus summation of all the loop gains. So you have to find all the loops within the signal flow graph, plus summation of the product of non-touching loop gains taken two at a time, right? So you have to see how many pairs of non-touching loops you have in the signal flow graph, take their product and add them up, right? I'll illustrate this as an example so it'll be clearer. Minus summation of non-touching loop gains taken three at a time. That means you have to see how many how many such loops are there, three in number, which don't touch each other, which don't have a node in common. And then you have to take their product, and add all of such products up. So this will continue non-touching loop gains, and it has alternate signs here: one minus, plus, then minus, then plus, and so on and so forth. So this is your delta. This is the denominator here. And what is delta 1 or delta 2? That is what is delta k. So delta k is delta formed by eliminating those gains that touch the kth forward path. So you have to find delta for the modified signal flow graph, which you obtain by removing the kth forward path, right? So once you remove the kth forward path, that means, for example, in this case, you remove the first forward path, and whatever is left for that signal flow graph which is left, find delta, and that delta would be delta 1. Similarly, remove the uh, second forward path, that is T2, from the signal flow graph, and whatever is left for that, find delta. That delta would be delta 2, and delta is to be found from this basic formula. So I hope it is clear. Now let us take an illustrative example, and this will help us uh, in actually understanding what we have written. So this is a block diagram for a system which has a number of blocks, and we want to, it's a multiple subsystem system, and we are interested in finding the transfer function CS by RS for this, right? So now how do you do something like this? The first thing that you have to do is to make the signal flow graph for this system, right? So how would you make signal flow graph for this system? For that, we have to label all the signals that you think are present. So wherever there is a processing of signals, just label. So for example, you have RS here, it is labeled. Here you can label this signal which is processed by GS, you can call this X1S. And then when you add this through the summing junction to another signal, here you'll have another signal X2S. This X2S is getting fed to the feedback path, and you can have, say, for example, X3S here, right? In a similar way, this X2S is then processed here. You will get X4S here, right? And then you have this summing junction. So this signal you can call X5S. Again, you have some processing. You call this X6S. This is already labeled CS, and this can be called X7S once it is processed by HS. Similarly, this X5S is taken up by H2S and then it is fed back, so you don't need to add it. And yes, you also have this signal here, which is the result of RS and X3S getting combined. So you can call this X0S, right? So X0S you pick up and you process it, and then you also, once you process it, you get X8S here. So this will add redundancy labeling like this, but then the next step would be then simplifying the signal flow graph that you have for this purpose. So how do you do that? Now let us label all the nodes that we have in this. So for that, we'll have to see all the signals that we have, and then label the nodes according to the signals that we have present in this. So let me draw the signal flow graph for this. Okay, so we have this here. So let us label all the nodes first. So this is my RS, right? This is my X0S, X1S, X2S, X4S, X5S, X6S, and then I have this is my CS, right? Okay, so then I also have processing of, let me see if I can label some other nodes up. So I have X3S here, right? X3S here. Uh, then I have, let me draw it slightly towards, okay, let us first complete this much. Okay. So RS and X0S, you just have basically RS getting added, because from this you can see that X0S is actually RS minus X3S, right? So that means to make X0S you have to add XRS and you have to add X3S, right? So X3S you multiply with -1 and RS you multiply with 1, right? And add the two together to get X0S. Then X0S is processed to get X1S and you call that G1S. That process, that system is G1S. Then coming to X1S and X2S. X2S from this diagram here, X2S is going to be X1S minus this signal here, right? So this signal here we have not labeled, but let us call this X5S into H2S, right? H2S. So that means, let me write it slightly neater, in a neater way. So this summing junction that we have to the summing junction here that we have to illustrate, right, using the signal flow graph, has this X1S minus, I'll leave the S so that it is easier to write. So it is X1 minus x5 h2, right, is equal to x2, right? So x1 minus x5 h2. So I have this x5. I have to multiply this with minus h2. Sorry, I have to multiply it with minus h2, right? I have to multiply this with minus h2s, right? So once I do that, and then I multiply x1s with 1, I get x2s. So this x2s, then the value of the node is equal to the sum of the incoming signals, which is x1s into 1 minus x5s into h2, and this is what I have here. So here we could have, actually labeled this as some other signal here, right? Then we would get an additional signal which would have to remove later on, but somehow I did not do it like that. This is also okay. Then this x2s gets processed again. It gets multiplied with g2s, right? So x2s gets processed, it gets multiplied with g2, gets multiplied with g2s, and you get x4s, right, here. And this x4s again, now so you have another summing junction. So let us look at this summing junction that you have here now, this one. So here you have basically the output is x5, right? And x5 is equal to x4 minus x7, right? So x5 is equal to x4 minus x7. So you have x7 somewhere here, right? Let us make x7 here, x7s, and then you multiply x7 with minus 1, right? So you multiply this with minus 1, and x4 you multiply with 1, so you multiply this with 1, and you get x5, right? So this is x5 is the sum of these signals, x7 minus x4. Now coming to the next part, which is this G3s. So you have this G3s here. So x5 gets processed with, you can multiply this with G3s to give you x6, and another summing junction here where you're adding x6 and x8. So x8 is obtained by taking this basic signal uh, x0. X0 you're taking up and you're multiplying this with G4. So from here you have, sorry, you have a branch going like this, right? You are multiplying this with G4s, right? And then this becomes x8 actually, right? And that x8 gets added to x6 to give you CS. So this becomes, can make your x8 somewhere here. This is your x8s, and then you multiply this x8 with 1, multiply this x6 with 1, and this gives you your CS. And then your CS, you're basically picking up, processing it by multiplying this with uh, the system that is being multiplied is h3s. So CS into h3s gives you x7s, which is here. In a similar way, you are picking up x2 from here and you are multiplying it with h1s to give you x3s. So this is h1s. So h1s. Okay, so this, then your CS, you can actually make a file block if you want like this, or leave it. It's not required, so you can just leave it like that. So this is the signal flow graph. Now, I think we have covered all the loops up. Now, how, yeah, you can simply, the next thing is to simplify it, because a number of nodes can be combined. Like you can you can combine these two. You can combine these two. You can combine these two. So you can remove the redundancy, right? So if you draw it again, you don't need to draw this x1. So you have rs, you have x0, right? And then you just have g1s, and from g1s you straight away reach to x2s. Then you have a straight line again, so you remove this x4s and you come directly to x5s. And here you have in the I did I forget to write this down? So this was h2s, this gain. Yeah, where you multiplied x5 with h2 to give you uh, yes. So this is h2s, this gain in the reverse direction. So you can draw this one here. Okay, I'm used to drawing the arrows at the end. Right, so this is your h2s here. In a similar way, you have this loop here, so you can draw this like this. So this is your from x2 to x0, you have h1s, right? Then you can also combine these two here. So from x5, you can move directly to, sorry, you can move directly to CS. So this is your CS, and you have G3S here. From you can combine these two here by eliminating x7s. From CS, you're taking a feedback which is equal to minus h3 minus h3. This feedback is also not h1s. This is h1s into minus 1. So this is minus h1s, right? And then you have this big loop outside from x0 to, you can combine these two signals here. So from here you can go like this directly to CS, this big loop, and you can call this is your G4S. So I think this is clear. This one is also uh, this is this one is H2. This was minus H2. I'm sorry, because you have a minus sign here, right? It was H2 into X5 minus X5. So this is minus H2. So I think it's okay now. This is G1 minus H1, G2. This one is G2S, right? This is minus H2S. This is G4S. This is G3S. This is minus H3S. So this is now a very simple signal flow graph. Now let us move this slightly down and look at the forward paths that we have in this, right? And the loops that we have. So the forward paths are very obvious. One forward path is this one. You can straight away move like this. The other forward path is you can move like this, right? So the forward paths, you can call this, you can call it T1. T1 is the forward path gain is, so K is equal to 2. The number of forward paths is 2. And the first forward path is G1, G2, G3. I'm leaving writing S for the moment. The second forward path is when you move directly from RS to CS. This is a gain of 1, right? So you could even eliminate this node and write RS here straight away. Anyway, so so the other forward path is G4, right? And so these are the forward paths. Now, what are your loops in this? So you can see one loop is this one, right? The other loop is here, right? Two of them here. The third one could be if you start from here, go like this, and go like this, and come back to this place, right? So let me draw this again. So these are two loops. Uh, let us draw the simpler loop. The third loop could be this one, right? So these are the three. The fourth loop, if you need to see it, slightly closely, let me draw this with another color. So this is the fourth loop. It's going like this, going like this, going like this, right? And then so you're able to finish the structure. So if you write down the gains, the loop gains minus G1 H1, this one, minus G2 H2, this one, small, this one, minus G3 H3, and this complicated loop that you have G4 into H3 into H2 into H1, with a minus sign. So G4 into minus H3 into minus H2 into minus H1 minus H1. So which is minus G4 H1 H2 H3, right? So this has a negative sign, doesn't it? So let me check once more whether we have done this right. H3 has a minus sign, H1 has a minus sign, yes, it's negative. H2 has a minus sign, yes. G4 is positive. So G4 into minus H3 minus H2 minus H1. So these are the four loops. Now what are the non-touching loops that you have? Any loops that are non-touching? So non-touching loops are which pairs are non-touching? So minus G1 H1 and minus G2 H2, not G2 H2, sorry, G3 H3 are non-touching. So these two loops, the small loop here and the small loop here are non-touching. Others, all the loops are touching each other. So the big loop is touching every other loop, and this G2 H2 is also touching. So you have only two non-touching loop pairs, right? So you can write down your delta. Your delta is 1 minus summation of loop gains. So your loop gains are minus G1 H1 minus G2 H2 minus G3 H3 minus G4 H1 H2 H3 plus summation of the non-touching loops taken two at a time. So you have to multiply these two. So you have only one, so you have plus G1 H1 G3 H3. So this is your delta. You can simplify this and write this as delta is 1 plus G4 H1 H2 H3 plus G1 G3 H1 H3 plus G1 H1 plus G2 H2 plus G3 H3. So this is your delta. Now let us look at delta 1. Delta 1 is obtained when you remove this T1 from the uh, from the graph, the first forward path. So if you remove this, let me first remove the other things that I have drawn here, right? So if I remove the first forward path from the drawing, from the signal flow graph, what is left? So I have to remove G1, G2, G3. So I have to remove G1 means I have to remove this node, this node, this node, right? This node, this forward path, this whole thing, right? So I have to, from RS to CS, this whole thing has to be removed. So if I remove this, is any loop left? Because I'm concerned about loops, right? So this small loop is gone. This small loop is gone. This loop is also gone. Uh, is the bigger loop left? No, it is not left because it is touching these nodes. So when these nodes are gone, the big loop is also gone, right? So although you feel that this big loop is there, but since these nodes are not there, you have to remove the nodes as well corresponding to the first forward path. That means no loop is left and delta 1 is equal to 1, right? Now, the other thing is the other delta is delta 2. Delta 2, you have for looking at delta 2, you have to remove the uh, the second forward path, right? Just let me see whether I can do that. Yeah, yes. So the second forward path is G4. So if I remove G4, I have to start from here, remove this node, and remove this node. So I'm still left with what is not colored in. So I'll just color this in blue. So I'm removing this, I'm removing this whole thing, I'm removing this. So I'm still left with, although I'm not left with this loop because this node is gone, I'm not left with this node because this node is gone, but I'm still left with this loop in between, right? I'm left with this loop in between. I'm not left with the big loop here, this one, but this loop is untouched. So delta 1 is 1, delta 1 is 1, but delta 2 is 1 minus summation of loop gains, and that loop gain is 1 minus G2H2, right? 1 minus G2H2. That is 1 plus G2H2. So now what is my CS by RS? What is my transfer function? T1 into delta 1. So T1 was G1, G2, G3. So G1, G2, G3 into 1 plus T2 into delta 2. And what is T2? T2 is G4 plus G4 into 1 plus G2H2 divided by delta. And delta is given here. So delta is 1 plus G4 H1 H2 H3 plus G1 G3 H1 H3 plus G1 H1 plus G2 H2 plus G3 H3. So this is your CS by RS. So I think now with this illustrative example, the application of Mason's gain formula for reduction of multiple subsystem systems is clear. Thank you very much.